Okay, so I realized from the previous video drawing was probably gonna help. So I'm in the drawing board right now. And we have the same circuit from before, I just changed the values, so they're 5 ohms now rather than 10. And what we saw was that the voltage was divided at this node right here. So I take a multimeter and measure here, it's actually going to be 5 volts. And across this resistor here, we were also going to measure 5 volts. Another way to draw this is people like to do just a plus here. We can call this VR1. It's going to be equal to 5 volts. And the voltage across VR2 is going to be 5 volts. And let me get into Kirchhoff's voltage rule. And it's basically just a derivation of the conservation of energy. The voltage in this system, if you add them all together, so if we add V1, VR1, and VR2 together, we should end up with 0. So let me draw that. I'm just calling this V1. And this is the math behind it, basically. And the way you do it is you start at a point. Let's just start at this point. I'll draw this in red. Let's just go around the system. So, okay, so we're hitting it. We're hitting the resistor from the positive side here. So what we can do is do plus VR1, and then we continue down. We're hitting this component from the positive direction. So we can do plus VR2, and we continue. We want to hit our original spot of the point right here. And this is, we're hitting it from the negative direction. So this is negative V1, or V inputs. And then we get to our original point here in the corner, and that's all equal to 0. We can move this over by adding VI on both sides, and that gives the equation right. And we know from LT-Spice that this one was 5 volts, and this one was 5 volts, and the original one was 10 volts. Let me draw that a little cleaner. So, and that makes sense, right? We have 10 volts, and okay, it's getting a little messy, so let me just erase some of the stuff. If we're starting at this point, we have 10 volts here at this node right here. So we could connect a resistor like this if we wanted to. And now we could actually use Ohm's law, because there's 10 volts on this node, and we know the ground node is at 0 volts. So if we take a multimeter probe here, we have 10 minus, and we take the potential difference of 0 here, it's going to be equal to 10. So we have, let's just call this R3, then VR3 is equal to 10 volts. And that's why Kirchhoff's voltage rule is sometimes called the loop rule, because it applies to a loop. So if we do Kirchhoff's voltage rule and we sum up all the components like we did before, we're started this corner, and we're moving through the circuit, and we're hitting this from the positive side. So we can, so I'm going to write out plus VR3, then we're going to continue moving. We're hitting our source from the negative side. See the negative sign right there? So it's minus 10 volts is equal to 0. And if we move this onto this side, we get VR3 is equal to 10 volts. And we've completed the loop. And remember, in the previous example we went through this loop. So let me draw the two loops out in different colors. So this is the orange one. Actually, let me clean this up a lot more. Okay, so these are two. I'm going to draw the first one in blue. So this is one loop, and the other one in pink. So this is our second loop. So that's kind of how the formulas apply. So you've probably noticed all the terminology. So let me write them out explicitly. You have a node, and that is the point. So a node is a point, and then let's just say I drop my pen here and I move down the wire, boom, and I hit this component right here, so I stop, and then I have to go the other way, and I go and I move until I bump into something else. Bump. So I bump into this component. So this is one node. Let's just call this one the plus 10 volt node. Let me use a different color. So let me just choose an arbitrary node here. Boom, we bump into this component. We go back and we bump into this component. Okay, so this is another node. We can call this node anything. We can call this Vx. And then use a third color. I just drop my pen. I move, bump, I hit a component, so I go back and I go this way. I can go down, bump, and I can go up, boom. Okay, so this is my third node. And let's just name this ground, do the ground symbol here. And we know that ground is always at 0 volts. So this simple kind of circuit right here has 3 different nodes. So hopefully that helps you kind of find, maybe I can give you another example. Let's just do another example. Okay, so how many nodes does this particular circuit have? So let's just start off putting our pen anywhere. Boom, we hit a component, we go back. Boom, we hit a component, we go back. Boom. Okay, so we have one node here. And we can call this, if this is VI, we can call this the VI node. Let me just take another color and drop my pen somewhere arbitrarily. Boom, hit a component. Boom, hit a component. Okay, so this is another node. Let's just call that VX. Let me use a different color. Arbitrarily just drop my pen here. Boom, I hit a component. I hit another component. Let's just call that node VY. Finally, I'll just drop my pen here, move up, I hit a component. I hit a component, hit a component. Boom, okay, so that's another. Let's just call that ground. So we have 4 nodes in total in this circuit. We have VI, VX, VY, and ground. So if I tell you, okay, there's something wrong at the VX node, you're gonna go, okay, so that's here. So something's happening at this node right here. If I tell you, there's something wrong with the VI node. Okay, so that's here. That could be anywhere. That could be here, here, or here. So hopefully this helps you a little bit with the terminology. Same thing with the loops. So in this case, it's quite obvious. We have one loop here. In this example, it's actually a little bit more complicated. Because you would think, okay, we have 2 loops. And that is true. We definitely have at least 2. So let me draw them to make it a little bit more explicit. We have the first obvious one. We have the second one. But we also have this kind of third one going like this. So we actually have 3 loops here. This is going to be important when you do Kirchhoff's loop rule or the current rule or other types of circuit analysis. Finding nodes in the loops is going to be really important, so make sure you practice that and get good at that. There's so much to talk about. I don't want to drag these videos out to make them too long. And there's just so much to cover. You can go in every direction. But I covered, in this video, I covered some of the terminology, and I covered Kirchhoff's voltage rule. So just to recap the voltage rule, it's basically you go around a loop. Let's just go this one. And you have to hit the components from the right direction. So this is positive right here, and that's kind of self-explanatory from the symbol, which means that this is going to be a high potential node. right? So current is going to go that way. So we can draw the voltages across these components like that. Just call this VR1, VR2, VR3 plus VR4. Let's just do the voltage rule on this loop right here. Okay, so let's just start here. We'll go down, so that's plus VR1. We'll hit the other one, so that's plus VR2. And then we go back, we hit from the negative side, so that's negative VI. And then we come back. So that's one loop, and this is all going to equal to 0. Let's do that rule here. Okay, so let's just start here. We go down here, so that's plus VR3 plus VR4. Notice that we're hitting this one from the negative side. So that's minus VR2 minus VR1. And we're coming back to our starting point, so that's all equal to 0. And you can kind of solve this a little bit. So well, basically I just moved these two terms over to the right hand side by adding VR2 and VR1 on both sides. So that gives us that. Let me just write it out explicitly. Okay, so VR2 plus VR1, that's these two components. The voltage across both of those is the same as the voltage across both of these. So that kind of makes sense, because if we take a multimeter here, let's just say this is 10 volts. So you have 10 volts on this voltmeter and 0 here, because this is ground, right? So the difference, whether you take it here or here, is always going to give you 10 minus 0 equal to 10 volts. So we know that the voltage across both of these are the same. But keep in mind that if the resistances are not the same, then the voltage at these points are going to differ. But this equation still holds true. And I'll show you what I mean in a little bit more advanced example later. Okay, so in the next video we're probably going to be looking at the Kirchhoff's current rule. Might be looking at some parallel connections as well. So yeah, thank you for tuning in. I hope these videos are helping. If not, let me know what I can do better. Let me know if there's anything that confused you, anything you want clarified, and I'll do my best to help you. And I'll see you in the next video.